For this next section, we have the comparison tests, and this is section 11.4. Now in 11.8, we actually had a comparison test for convergence and divergence there. We actually called it the comparison theorem, and this works in a very similar fashion. There are many series for which the integral test itself will not work, and I could arguably try to translate them into an integral and use comparison theorem there, but in order to draw a conclusion from there, they would also have to first satisfy the conditions of the integral test. So if I had something, for example, like sum from n equals 1 to infinity of cosine of n squared over n squared, I would not be able to translate this into an integral. Well, I mean, I could, but I wouldn't be able to draw any conclusions from the result of the integral test because technically this doesn't satisfy the conditions. It would turn into a positive and continuous function, cosine of x, quantity squared divided by x squared, but it doesn't satisfy the decreasing condition. Notice that depending on what kind of an input I have for x, f prime of x can vary wildly between positive and negative values. So what I have instead is I have a comparison test. So the comparison test, or direct comparison test, if you're given a series of positive terms, sum of a sub n, and you have another series of positive terms, the sum of b sub n, then if a sub n is less than b sub n for every term, or at least eventually every term, and the sum of b sub n converges, then so does the sum of a sub n. Because of positive terms, the sum of b sub n converges, so those terms go to 0, and hence these terms of a sub n go to 0, and since the b sub n terms are bigger, whatever sum the b sub n terms add up to has to be larger than whatever sum the a sub n terms sum up to. And similarly, if b sub n is less than a sub n for every n, or at least eventually, then if the sum of b sub n diverges, then so does the sum of a sub n, because those terms are all larger than something which ends up diverging. So for our series up there, I couldn't use the only test I had so far, which was the integral test, but I do know something about part of my series. I know that no matter what, cosine of anything is going to be between -1 and 1. But since I have a cosine of n squared there, that means I can only have positive values. So cosine squared of whatever I put inside is always going to be between 0 and 1. But that means the terms of this sequence, or the terms of this series, a sub n equal to cosine of n squared over n squared, these are all positive terms. But since cosine squared is less than 1, I can replace that with a b sub n equal to 1 over n squared, which will be greater than cosine of n squared over n squared equal to a sub n. So my b sub n's are larger than my a sub n's, but the sum of b sub n we learned last time is equal to pi squared over 6. This converges. So since I found a bigger series which converges, that must mean that my original series converges. So I would say the sum of cosine of n squared over n squared converges by comparison to the sum of 1 over n squared. And this works both ways. I just have to be careful about how I choose things. Take a slightly uglier example. 4 over 2 to the n plus 6n squared from n equals 1 to infinity. Now when I look at these things, I generally want to look for whatever's the biggest deal in my series. So here, I only have a 4 on the top, but in the denominator I have a 2 to the n. And then I have a 6n squared. We should know from practice, or at least learn from practice, that 2 to the n is actually going to be bigger than any polynomial. So I want to see what happens if I get rid of that 6n squared. But if I get rid of that 6n squared, that will mean I have a smaller denominator and therefore a bigger fraction. So this original series is smaller than the sum from n equals 1 up to infinity of 4 divided by 2 to the n. And if I factor this 4 to the outside of the series, now I have a geometric series with the common ratio of 1/2. And I know that that converges. In fact, I know what it converges to, because it's going to be the first term, 1/2, divided by 1 minus 1/2. Or simply 4 times 1. But sometimes I need to study what I have and strictly face towards a certain goal. This series, for example, I have an n over an n squared, and I've got some extra constants added on, or maybe some other stuff. So I would expect comparison to n over n squared, or 1 over n. But this might be difficult to do with the direct comparison, because I need to find something. Let's see, if I want to compare to 1 over n, I need to make this series smaller until it looks like 1 over n. Basically, I need this series, my original, to be larger than the series of 1 over n, because that's what I need to declare divergence for the comparison test. This type of inequality is not clear immediately, and I have a couple of techniques at my disposal. I should add a question mark. I could ask the question and then verify. So repeating the question, I could cross multiply. I'd be asking, is n squared minus 4 less than n squared plus n? And that's certainly going to be true for all positive n. But to be a little bit more rigorous, I should start with my original term and try to make it smaller. Well, I have a plus 1 on the top. I can easily make it smaller by getting rid of that plus 1. And at this point, I could probably, arguably, turn it into an integral test where I do a partial fraction decomposition. But that sounds like work, and I hate work, so I'll try to shrink it again. I have an n squared minus 4 in the denominator. So what happens if I get rid of that minus 4? Well, I end up getting a larger denominator. And if I have a larger denominator, then I have a smaller fraction. So this turns into the smaller term, n over n squared, which is equal to 1 over n. But the sum of 1 over n diverges. So I can say that the sum of n plus 1 over n squared minus 4 from n equals 1 to infinity diverges by comparison to 1 over n. But I have to be very careful with problems like this, because if my inequalities aren't laid out in the right direction, you might end up saying something you don't really want to say. So let's say I switch the signs around on this problem. I'll have n minus 1 over n squared plus 4. But now if I look at n minus 1 over n squared plus 4, if I get rid of this minus 1, that's going to make the top bigger. And if I get rid of this plus 4 in the denominator, that's going to make the denominator smaller, and therefore the fraction bigger. Well, that was silly. 1 over n. Which is totally unhelpful, because now it says that my series is smaller than 1 over n, so it's smaller than something which diverges. Which could be literally anything, because not only is 5 less than infinity, but so is infinity. There are different sizes of infinities. I can have two divergent series, but one will diverge worse than the other. But I really, really think that this should be compared to 1 over n squared. So what I have as an improvement, actually a very vast improvement to the direct comparison, is the limit comparison, which is the far superior test, because anything that the direct comparison test works for, the limit comparison will work for. And the limit comparison will work for things that the direct comparison doesn't work for, like this series I just wrote out previously. So the limit comparison test, given a positive term series, sum of a sub n, and another positive term series, sum of b sub n, if the limit as n goes to infinity of the terms a sub n divided by b sub n, so we're comparing their sizes as n goes to infinity, if this is equal to some number c, which is not 0, and is of course not infinite, then the sum of a sub n converges if and only if the sum of b sub n converges, which means they either both diverge or they both converge. Now there are some additional notes to this. Let's see. We'll say note. If b sub n converges and the limit as n goes to infinity of a sub n over b sub n is equal to 0, then the sum of a sub n also converges. What this limit being equal to 0 means is that a sub n is extremely small compared to b sub n as n goes to infinity, which means that a sub n's are actually smaller than my b sub n, so it kind of turns into a direct comparison. And similarly, if the sum of b sub n diverges, and this limit is infinite, then the sum of a sub n also diverges. Because that says that a sub n is significantly larger than b sub n as n goes to infinity. So it again turns into a direct comparison, and if b sub n diverges, then so must the a sub n. So why don't we do this to the sum from n equals 1 to infinity I think I made a small error earlier of n minus 1 over n squared plus 4. Let's check on the earlier series. Yeah, right here. I should have started this at n equal to 3, because if n is equal to 2, I'm dividing by 0. Should be more careful writing out these series. So I've already shown that the direct comparison doesn't work on this, so I'm going to try the limit comparison. And the big deal here was I had an n over n squared, so I'll try to limit compare to 1 over n. Typically, I put my comparison series on the bottom of the limit, but it actually doesn't matter. So I want to evaluate the limit as n goes to infinity of my original n minus 1 over n squared plus 4 divided by my new 1 over n. And I'll simplify my fraction. I'll have n squared minus 1, n squared minus n divided by n squared plus 4. And we've encountered problems like this before. I could either do L'Hopital's twice, or I could divide top and bottom by n squared, or I could try to read coefficients since this is like a polynomial. I'm going to choose this method, because now this is equal to the limit as n goes to infinity of 1 minus 1 over n divided by 1 plus 4 over n. But these go to 0 as n goes to infinity, leaving me with just 1. So this says that my series from n equals 1 to infinity of n minus 1 over n squared plus 4 must do exactly the same thing as the sum of 1 over n. But the sum of 1 over n, we should know by now, is divergent. So it wouldn't be a terrible exercise to take the limit comparison test and apply it to all of my direct comparison tests using the same series that I had used to direct compare. You'll end up getting exactly the same results. So, as a remark, the comparison tests can also help me a little bit with estimating sums, as long as I'm comparing to a series for which the integral test can be used. So if the sum of a sub n is less than the sum of b sub n by a direct comparison, or possibly even a limit comparison, although that's a little dangerous, and the integral test can be applied to the sum of b sub n, there's a function which is continuous, positive, and decreasing, which can be used to represent b sub n, then if r sub n is the remainder for the sum of a sub n, that is, r sub n equals the sum from 1 to infinity of a sub n minus the sum from 1 to m of a sub n, or just the tail of the series, and t sub n is the same for the sum of b sub n, it's the remainder after using the partial sum, we will have that r sub m is less than t sub n, because a sub n is less than b sub n, and t sub m is less than the integral from m to infinity of f of x dx, because this is the line that is the result of the remainder for the integral test on b sub m. Meaning I can use the upper bound for the error for t sub n as an upper bound for the error for r sub m. So if I wanted the error in using taking this first series I had before, cosine of n squared over n squared, if I were to find the error, or rather estimate the error, (100 terms of the sum from n equals 1 to infinity of cosine of n squared divided by n squared), I would use its comparison series, n equals 1 to infinity, let's see, cosine of n quantity squared over n squared was smaller than sum from n equals 1 to infinity of 1 over n squared. But this was a p-series, something which the integral test always works on, because they'll be strictly decreasing. It creates a continuous function, 1 over x squared, which remains positive. Then r sub m, or r sub 100 I should say, would be less than or equal to the error in using 100 terms of 1 over n squared, which is in turn less than the integral from 100 to infinity of 1 over x squared dx. But this value, rather this evaluates to, it's x to the negative 2 power, so this is negative 1 over x squared, cheating the improper integral again. I end up with 1 over 100 squared, which is 1 over 10,000. So if I use 100 terms, I'm going to get at least 4 decimal digits. To kind of break ahead of some of the sections here, sometimes we'll have multiple steps to our process. If I have the sum from n equals 1 to infinity of just cosine of x divided by n squared, then the direct and the limit comparisons wouldn't really work out for this, because cosine of n, as n goes to infinity, it doesn't have a limit. So if I were to try the limit comparison, I would limit compare with 1 over n squared. I would not get a limit. I would get something which diverges. If I try to do a direct comparison, that wouldn't work, because not every term of this series is positive. But there is something called absolute convergence, which is a couple sections ahead, but it's still something we can technically use. I believe they also made mention of it in section 7.8, where if the absolute value of a series converges, so does the positive version. Or not the positive, but the regular version. So if I look at the absolute value of this series I wrote here, this is something which has positive terms, which means it can be compared. So that's something to consider if you're faced with an awkward problem in the future.